All right, welcome everybody to week 4 of IS50EP. Today we're going to be talking about how to do rasterization. One of the goals for this semester is to get you guys to a point where you kind of understand how game engines work. So if we can imagine this is like a screen, like, your screen is made of pixels, little dots that light up or not, in red, green, blue, and combinations thereof. And so the most common, if you want to do a triangle rasterization. No, we're going to do even simpler than that. We're going to do line rasterization first. So line rasterization means if you have a line, like let's say that you have a line and it extends off the edge of the screen even, right? And it connects. Let's see if I can draw a straight line between 2 points. Close enough. So let's say we have a line and part of it's off the edge of the screen, part of it's off the edge of the screen the other way. And you want to rasterize this. Rasterization means drawing the pixels that correspond to the line. First thing you have to do is clip it, right? So that whole thing up here kind of gets clipped off. Everything down here kind of gets clipped off. And then these points need to be drawn. But the question is, like you can see, this line is kind of covering, like there's more of the line in this pixel than in this one. This one only has like a little itty bitty fraction of the line. This one's got a lot more of the line. And so one of the problems, like one thing we could do is we could just color in every box that the thing goes through at all, right? So we can color this guy in and color this guy in and just kind of color everybody that is touching any of the boxes at all. But the trouble with this is that you're going to get this weird like stair step pattern. And as you get different lines in different directions, these stair steps become fairly obnoxious and obvious. This is a concept that is handled by something called anti-aliasing. So anti-aliasing, basically, if you have just an itty bitty touch of the line, like maybe this whole thing would have to get colored in. Maybe you colored in very lightly, so it just gets a little bit of the line or something like that. So anti-aliasing is the notion that as you draw a line across diagonals like this, the edges kind of get, areas that the line touches more of are darker, areas that it barely touches are lighter, and this causes it to look better. When you really zoom in, it looks bad, right? Because it looks like it's all blurred. But from a distance, what happens is here you can see these really noticeable stair step patterns, and then on the right you can see that there are, it looks like if you were to move your head back and look at it, it looks a lot better when it's anti-aliased. So your job for this assignment is I'm going to give you code that does line rasterization, okay? And maybe we can talk about the theory of it a little bit. Let's say that we've got a let's get a line segment that starts here and goes here, and it's traveling at a slope of 1. So let's say it goes here instead, just to, because these are not square cells. Just to make things even, we're just going to go exactly up one box to the northeast every step of the way. So how would you guys do this? How would you rasterize this line? Like, how would you write a for loop that would draw these pixels to the screen? Assuming you've got a function called like draw pixel. You've got a function called draw pixel, and it takes in like an x and a y coordinate. It'll draw like a little yellow box at that x and y coordinate. How would you draw these pixels on the screen if you're starting at, we're not going to use screen coordinates, we're going to use Cartesian coordinates, going from 0, 0 to 1, 2, 3, 6, 7, going up to like 7, 7, just to make life simple. This point here is 7, 7. So this point here is 0, 0. So how would you write a for loop that would do that? You've got your equation, y is equal to mx plus b. We're not using parametric linear line equations. M in this case is 1 and b is 0. So this equation is literally just y is equal to x. How would you write a for loop, that maybe starting at 0, going to 7, would draw all of these pixels on the screen? I'm going to think about that for a second. I'll pause the recording. Yep. So for this really simple case, you can just say for int I equals 0, I is less than 8, I plus plus, draw pixel II, and that'll draw all these wonderful 8 pixels here. More generally, though, this is the, what is that, the rows, that's the Y. So you'd have that I there be something like M times I plus B, and then this would just be I, right? Because if we're going, let's see, yeah, from left to right, yeah. So I would be the X value. So that would work, sure. So this is, in fact, I've got code that I've already pushed out to you guys for this. Let's go back into here and look at the solution. So here's the draw pixel function. It takes an X and Y location, and it takes an RGB, so you can choose which color you want to draw to the screen. I think I'm picking random colors to draw to the screen. And so starting at some X and Y location, going to some other X and Y location, it is going to draw all the pixels in between. All right. And this is just the M times X, essentially, plus B, essentially. So that's the Y equals MX plus B equation, and then it draws that X and Y. So if I run this, if I compile it and run it, going from like 2, 3 to 23, you can see that it draws a horizontal line here, like that. And if we go from 2, 3 to from 2, 3 to 23, there, right? 2, 3 to 23. Might be off the edge of the screen. Let's see. 0, 0 to 2020. See, it draws a nice horizontal line like that. Random colors for each one. Looks pretty good, right? But we got a problem. And the problem is, welcome, boss. Yeah, exactly, Megan. Set Y equal to the equation of the line, right? So you got your Y equals MX plus B, you plug in the X, you get a Y out. The trouble is that if we do from like 0, 0 to like 20, 40, our line starts breaking up. You see that? So as we're iterating across X, we're starting at X equals 0, X equals 1, X equals 2, X equals 3. If the slope is really high, then we actually get discontinuities in our line. We're not drawing a line anymore, we're drawing a dotted line, which looks pretty bad. So if we go from 0, 0 to, let's say, 5 across, 20 down, then it's really discontinuous, right? So, yes, exactly. You got it, Megan. You need to calculate when the line is steeper than it is wide versus wider than it is steep. And then you iterate on the y-axis. You go, Bruce, do you understand? Like, so in a case like this, instead of iterating from x equals 0, which is that guy right there, x equals 1, x equals 2, x equals 3, x equals 4, instead you do row 0, row 1, row 2, row 3, row 4, and then you'll get a straight line. So that is your assignment. Okay. So you've got working code, and the code looks fine. Like if we go from 0, 0 to like 22, 0, 0 to say 10, 5. We'll get a solid line when it's fairly shallow. But for steep values, instead of iterating from starting x to ending x, you should iterate from starting y to ending y. You're going to have to do a little bit of algebra to change this equation, y equals mx plus b. You're going to have to change that. You're going to have to solve for x instead, right? So subtract y from each, subtract b, sorry, from each side, divide by m, and you get x, right? So basically, you're going to, instead of iterating from 0 to 7 on x, you're going to iterate from 0 to 7 on y, and then compute each x value instead. And that is your homework due on Thursday. Yep. You hate it? It's just algebra. So you if the slope, you shouldn't have any gaps in your code. So the code that I'm pushing out to you guys is not good code. That's why it's a homework assignment, right? It's your job to fix it. So right now it reads in starting values for x and y. So 1 point here, 1 point here, and you want to draw a solid line between them. Okay. It's computing the slope. Is it handling vertical slopes? Nope, it's not. There's problems with this code, and you need to make your code work with vertical lines, horizontal lines, when it's steep this way, when it's steep that way. So when the 2 points are on opposite sides of each other, right now, if you have 1 point, like if your starting point is to the right of the ending point, it won't run at all, right? I don't think. As long as x starts at x1 and goes towards x2. So if they're backwards, it won't run at all, right? So, but this is starting code that works enough that, like, it can draw a pixel to the screen. It's got a for loop that figures out the slope, and so you've got something that's like halfway there, 3/4 of the way there, and all you need to do is fix this code so that the lines will rasterize properly, horizontally, vertically, steep, shallow, and backwards. Okay, that's your task. What's the homework? That's your homework. Okay, and this is using my colors library. So the colors library has functions like move cursor. So this is actually text output that looks like graphics, and you can use the colors library to basically draw a 24-bit color to the screen. If you want to get really fancy, you can do things like Kyoto. You use it for like image rasterization, things like that. So this is grabbing pixels from a photograph and drawing them on the screen. If I were to reduce the font size, then let's put the font size down to 9-point font. Do it again. You see we get more pixels. Now these are non-square pixels, so it's sort of deformed a little bit, and the program tries to sort of compensate for it, so it's not too distorted, but you can see it's still not quite perfect, right? If you, however, turn the font size down to 1, you actually do get square pixels, and then everything works a lot better. And you can actually rasterize a 4K image inside of Putty. Putty doesn't like this very much. Putty, I mailed the Putty developers. I'm like, hey, Putty tends to crash when I'm trying to animate 4K images inside of your text console window. I never heard back from them. It's kind of weird. But yeah, these are all spaces. These are all actually letters. So if I highlight these things, you can see these are actually letters. And you can see how slowly Putty updates to that as it's selecting, all these characters. But this is a full res, kind of image, and this is all text. These are just spaces that are colored. So Control L to clear the screen. At least works pretty well. Put the font back up. 22 point. I like making it big. My students can see it. So yeah, so the colors library has functions like move cursor, and that moves it to the given row and column. And then setting the background color, it takes 24-bit color, and then it just prints a space to the screen with the background color set to whatever it is, so it effectively gives you a pixel. So using this colors library, you don't need to use STL, you don't need to use DRM GUI, you can actually just rasterize things right to your Putty console. And this is a great learning device for learning how rasterization works and things like that. And it is flushing after literally every space, which is terrible. If you wanted to go faster, don't do this. Don't do this. This is not great. Okay, so we aren't greenfielding this like RTX yet. So this is substantially easier than RTX. So I hope all of you guys will be able to get that done. You guys understand? Anything else you need to know? Reset color kind of like gets rid of whatever background color you have set. If you don't do that, then this text here will have whatever background color was the last thing you outputted. moving the cursor back to the top left corner of the screen. Screen coordinates, the top left corner up here is 0, 0. So row 0 is the top row in screen coordinates. And then it clears the screen after you're done. You can choose it not to do random colors if you want. You can pick whatever colors you want, but this is a good little exercise teaching you a little bit of algebra, teaching you how to like rasterize something. Okay. So let's move past line rasterization because we got like half an hour left, and let's talk about triangle rasterization. And depending on how you guys do with a line rasterization, like if you draw a line, then you can draw a triangle. How? So triangle is 3 points, right? So maybe make a triangle. Let's do it like this. Let's do a really simple triangle to begin with. I almost hit it. Got a new tablet. It's not something exactly used to yet. Okay. So let's say this guy is at 0.00, this guy's at 0.100, this guy's at 0.55. You guys with me? We got a little triangle here. So if you wanted to do wireframe rendering, all you do is you rasterize the line here to here, here to here, and here to here. You guys with me? Like with the code, with this code, you can draw the outline of a triangle, right? It's just 3 lines. You guys understand? Sean? Raymond? Cyril? Yeah. You know, triangle's 3 lines, so draw the 3 lines, you're done. But let's say we want to fill the triangle, named after Mr. No, I'm kidding. Let's say you want to fill the triangle, okay? And fill in I want to fill it. Go to a gas station, ask for a Phillip. That's a joke from a Brandon Sanderson novel. So to fill a triangle means that all of these points, you know, if I were to draw another one of these things over there on it, we want to fill all of the pixels inside of the triangle. And there's a couple different ways we can do this. I'll show you 2 different ways of doing a triangle fill. All right. So the sort of standard way of doing it is you will iterate, let's say, down the rows, right? So we've got rows coming down this way, also known as Y, right? And so what you do is you get the, like, let's say we're on this row. You just fill 1 row at a time. It's not very horizontal. Let's try that again. Do 1 row at a time. And you just basically go down to the next row, and then you fill all of those pixels in there. You guys understand? So if I were to superimpose a triangle over this. Like that. If I can line it up right. Come on. Snapping. It's snapping from one to the other. So my lines are now like right on the edge. Whatever. Okay, so we're gonna fill all these pixels in here. Then we come down here and fill in all these pixels here. Then we come to this one, fill in all these pixels here. You guys understand? So you just do each row one at a time. Well, how do you know what the column is? Well, x is equal to y minus b divided by m, right? So you've got a line here. So the y-intercept is 0, the slope is 5, so or the slope is 1, rather. The slope is 1. And so it's just going to be x is equal to y, and so at 3, 3. So when you're at row 3, the x is equal to 3 as well, and we fill that spot in. Okay. So yeah, Megan's already done. So. Okay, but we're not doing this for this week at least, or at least this homework assignment. So what you do is you figure out the starting location, you figure out the ending location. Both of these could be computed algebraically. This guy has a slope of -1, so m is equal to -1, and the b on this is 10, And so for this guy, x is equal to y minus 10 divided by -1. So with y equal to 3, it's -7, which equals 7. And so we come over to x is equal to 7 on this one. That's not a 7, that's a y. Let's try that again. Yeah. You guys understand? So when we plug in 3 for y, 3 minus 10 is -7. -7 divided by -1 is 7. So x is 7 on this one. And so we iterate from x equals 3 to x equals 7 on this so for row 3, the columns are going to go from 3 to 7. And we just fill it all in horizontally. Okay. Does that make sense to you guys? So basically you've got a line equation for this, got a line equation for this. The bottom is flat, which I picked deliberately to ignore any random things. So you just basically just fill in all the things. You figure out the starting x, the ending x, and just fill across. And then you can fill in a triangle. Now you might ask, well, what if we had a triangle that looked like this? It's a pretty gnarly looking triangle, but you know what I mean? Like, let's say it isn't horizontal on the bottom. Well, you can split it such that it is horizontal on the bottom, and you fill this top here, and then you split it so that it's horizontal on top here, and you fill basically this triangle, the upper triangle, you fill the lower triangle separately. Yep. So no matter which triangle you get, you can draw any kind of triangle you want. You can always, this tablet's killing me. You can always draw a line such that you have a flat bottom. And, if you have something like this, you got a flat top. So every triangle you have either has a flat bottom or a flat top. And if it's not, if it's at some weird angle, then you just split it. Now you got a flat top and a flat bottom on the two. All right, thank you. I don't know. This. If it's like that, then you would split it here. Almost. Split it here. There we go. Close enough. You guys understand? So that algorithm works, basically the same way. If you have a triangle that doesn't have a flat bottom or flat top, you find the midpoint. Whichever one of these points is in the middle, you draw a line across, and then you fill the top half and the bottom half separately. That's kind of the standard way to do triangle filling. Now, let me show you a different way of doing a triangle fill that involves the power of cross product. Okay, and this will be useful when we start talking about convex holes. Okay, so do you guys understand this, Voss? Does that make sense? Yeah, you split whichever one. You have 3 vertices, right? Whichever vertex is vertically in the middle, that's the one you split on, right? If 2 of them have the same horizontal location, then you don't need to split. It's like if your whole triangle was just this guy. If the 2 of them have the same row, you don't need to split it at all. You're done. But if you have 3 different y values, like this is y is equal to 1, this guy's y is equal to 10, this guy's y is equal to 30, then you split on the middle one. And you make an upper triangle and a lower triangle. Okay. Cool. Raymond, Bruce, you guys understand? So after you do line rasterization, we'll move on to triangle rasterization next. Line rasterization hopefully is not going to burn your brains too much because you've got working code, like I said. So let me show you the cross product way of doing this. And this is maybe going to be a review for some, maybe it'll be new for some of you guys else. So cross product, if you've got a vector, you got another vector, a lot of times in video games, you want to know, is this vector to the right? In other words, is it clockwise? Is it clockwise? Or is it counterclockwise? Or concealed carry weapon of the first guy? You guys understand? Or anti-clockwise, as the Brits call it, anti-clockwise. So cross product will tell you if a thing is to the right or to the left of something. All right. So you've got a couple different possibilities with cross product. This is called scalar cross product, by the way. Actual 3D cross product gives you a new vector who's at a right angle to the other two. So if you have two vectors, the cross product will be this guy. So if you have a triangle like that, the cross product is actually the normal vector. So the vector cross product is used to get the normal vector of a triangle. If you ever wondered, how do I know what the normal of a triangle is? You just cross product the two basis vectors of the triangle, and you get the normal. Nice. We're not doing that right now. Okay. So so we want to know, is vector 1, vector 2, is vector 2 to the right of vector 1? If they're pointed in the same direction, then we will get a cross product, a scalar cross product of 0. If they're pointed in opposite directions, vector 1, vector 2, we'll get a scalar cross product of 0. If we get it kind of depends on the order that you do the multiplication, right? Because it's not, what's it called, commutative. But generally speaking, if you have vector 1 here and vector 2 is clockwise of it, you are going to get a negative number, like not negative 1. Negative 1 is like perfectly perpendicular. It would be negative 1. This is going to be a negative number because it's pointed off to the right. And if you have vector 1 and vector 2 is kind of pointed this way, you will get a positive number. Okay. So how does that help us fill a triangle? Or for a triangle, we really don't need this algorithm, but if you have like a convex hole or something, convex hole looks like this. You can use this algorithm to fill a convex hole without splitting it into triangles, which is usually what ends up happening. I have to split it. Again, apologies, my lines aren't quite straight. You would have to split the convex hole like this and then fill each of them triangles. Depending on your needs, this algorithm can be faster. So we've got a convex hole laid out clockwise. Same algorithm applies to a triangle if you have it laid out clockwise like that. We want to fill all the points inside of it. Same algorithm. It's just triangle has 3 sides. This convex hole has 1, 2, 3, 4, 5, 6. This one has 6 sides. Okay. So anti-British. Cross product can be used to tell if a point is within the convex hole. If it is, we fill it. All right. So let's say that we know we have a AABB. Do you guys remember what AABB stands for? AABB. AABB. Anyone remember what that stands for? I'm just going to draw it on the convex hole, but it is a German aligned axis line. Nice, very nice. I love it. All right, yeah. Don't leave out Japan. You know, Japan was on the axis too. Okay, so let's say we have an AABB and it looks like this. Close enough. Whatever. You know, it'll be a little bit tighter here, but you know, you guys get the idea. So we've got an AABB that wraps this convex hole. Now, last time when you did RTX on, you were doing things like testing to see if array. Did I erase it? You're testing to see things like, did array hit the box, right? And you plug in y equals mx plus b, you get a collision there. Congratulations, it hit the box. But like I told you last time, when you do intersections, you can do approximate intersections, or you can do exact intersections. And when you have a skeletal mesh or a static mesh or something like that, you will have convex holes that actually wrap the thing more tightly. And you want to know, did I hit this convex hole? So it's quite common to have just little AAB wrapping it, because then if you miss it, it's very easy. Done, miss, who cares? We're done. But now we want to know, is this point within the convex hole? Right. Is any point of this line within the convex hole? Something like that. So how do we tell if something is within a convex hole? Like this point right here. point P within the convex hull. And we've got vertex 0, vertex 1, vertex 2, vertex 3, vertex 4, vertex 5. And they're all laid out clockwise, not anti-clockwise. Sometimes people do it anti-clockwise, counterclockwise, and then the math is just the opposite, right? So check it out. Do you guys know how to make a displacement vector? So if I take the point P and I subtract V0 from it, this creates this vector right here. Okay. You cross product, yes, perfect. Very good. Yeah, that's exactly right, Sean. So a displacement vector will give you and that's basically the direction from V0 towards P. Like that's the direction I would have to drive in. If I was at V0 right now and I wanted to go to P, this gives you both the direction and the distance. Displacement vectors is something called a displacement vector. They commit evil with direction and magnitude, right? So in this case, we're not using it for anything other than a cross product. So we've got one displacement vector, which is V1 minus V0. That is this line right here. I'll draw it in red, kind of highlight it in red. That's that vector. And then we've got P minus V0, which is this one. And if we cross product the two of these guys, if we get a negative number, that means that P is to the right of it. Okay. Now, we'll get P is to the right of it if P is over here, right? So we're not done. We have to do this for all of the vectors, right? Because if P is to the right, it's to the right of V1. If it's to the right of V2, if it's to the right of V3, if it's to the right of V4, if it's to the right of V5, then congratulations, it's inside of the convex hull. You guys understand? And then we can fill that point if we want. Or, this is actually useful for more than just filling, right? So like I said, if you want to fill something, the default fill algorithm is pretty good. You can use this to fill a convex hull, right? Like for every pixel inside of this AABB, starting at this X, starting at X min, going up to X max, starting at Y min, up to Y max, right? You can just go through every point inside of here, and for every point that meets this test, that is to the right of every vertex, then you draw that point, and then that'll fill a convex hull. Okay. It's a lot of cross products. For every point within this AABB, we're going to be doing 6 cross products or 6 cross products, right? Well, not if it's outside, we could probably stop, right? Like at this point here, it's to the left. We don't have to do any more. It's outside, right? So on average, we'll be doing, 3, I don't know, maybe something like that, cross products per point. And so that's fairly expensive to fill. It's a lot easier to just do a little bit of math here, do some MX, blah, 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 figure out the starting, figure out the ending, and just for loop across. No anti-aliasing issues except on the right. This convex hull system also might get rounding errors. Like you might have points. Like if you have a point like right on the edge, right? Are you going to get a positive or a negative? 50-50? I don't know. So you might be having holes like on the edges, right? So it's not necessarily a great method for filling, but this approach is very useful for telling, like, if you are inside of an object. Same algorithm, right? If you have a convex hull for your map, let's say, which is what you have in like Quake and things like that, they wrap convex hulls around all the platforms and things like that. You can very quickly say, hey, is this point solid? Yes or no? Is it inside of, you just do some cross products and you're like, yeah, that's lava, that's water, that's air, that's solid. It's a very, very fast, so many cross products. It's a lot of cross products. It is, sure. But for a simple point contents test, like if you're just like, hey, tell me about this point in space, then you have some sort of data structure that gets you down to this convex hull. Now, last time we talked about BVHs, right? Where you have like a box, and inside of the box, you have a box. Inside of that box, you have a box, and maybe inside of that, you have the convex hull. Okay, so with the BVH thing, you would be like, this point here is inside of this box, inside of this box, inside of this box. Okay, it's inside of it. Then you do the convex hull test. So you only have to do these cross products like once. So it's like, between 1 and 6 cross products. Yes, it's inside. Return true, it is solid. Or if you test this point here, you do maybe 2 cross products, return false, it is not solid. Okay, so very good, Megan. You've successfully completed Thursday's homework assignment. Triangle fill, right? Triangle fill. Megan nonsense. Fantastic. All right. Come on, catch up, the rest of you guys. Catch up. All right. But Quake actually does not use... so do you guys understand all this? Like, if you want to know if a point is inside of a convex hull, you just cross-product it with each of the... Right? So you take the displacement vector, the displacement vector, cross-product them, see if the sign is positive or negative. And if you're to the right of everybody, you're inside. Yeah, makes sense. Bruce? If you're to the right of everybody, then you're inside of the convex hull. Okay. Now, this BVH structure is the standard now, but there's another thing. What is the equation for cross product? For scalar cross product, it is x1 y2 minus x2 y1. So it's 2 multiplies and a subtract. It's not really that expensive. It is not too bad. And so to figure out, like, is this point within a convex hull here, you're going to run down the BVH tree, which is hopefully going to be like an order login algorithm. So if you have 1 million objects, you find in like 20 steps or less. And then once you get down to the convex hull, then you do maybe 6, in this case 6 cross products, and that's a total of, let's see guys, subtraction 7. 12 plus 6. So it's 4 cycles of multiply, 48 cycles plus. There's going to be 12 subtractions total, so it's going to be like 60 cycles to determine if a point is inside of a convex hull, plus the 20, so like 80 cycles. So you could basically tell if you have 1 million boxes inside of this world, and these boxes can contain convex hulls inside of them, basically you can find out if a point is solid or open or lava or water, because typically you mark this thing, right? Like you'll mark this convex hull as water. It's a water node, and everything inside of it's water. And so when you do a point contents test, it takes you 80 cycles and it returns water. That point there in the world is water. And then your renderer will draw it as water. Or like your game code can be like, am I underwater? Right? And so you pass in the point, you do a point contents test for your location. And if you are underwater, then it's like, now you're drowning, or you have an oxygen meter that goes down or something like that. And it's a reasonably fast lookup. Yeah, you can show that. Okay. But this is the equation for a scalar cross product right here. It's not too bad. It's not too gnarly. And then you just be like, what is this point? Water. All right, cool. And so we got 5 minutes left. Let me talk really briefly about another alternative to BVH, another acceleration structure. Called a binary space partition. Yep. This is what Doom and Quake use. All right. And so if you have, top-down view of a world like this, I don't know, warehouse over here, something like that. A binary space partition is a binary tree. You guys all love binary trees, right? And so what you do is you get a splitting plane, and how you find that splitting plane is complicated, because there's sort of infinite splitting planes you can do. But let me just make one up like this. So this is splitting plane 1. Build a tree over here. And let's just say it goes this way. So this is to the right, actually. Right, because the arrow is coming downwards, so that's to the right of it. And let's name this object A, and this object B, and this object C. And if we ever get to a place where one of our halves has only one object in it, we finish. And we make that a leaf node, and so this is a leaf node with just A in it. This could be a convex hole or something like that. This one over here has 2 objects in it, so we can split it again, like that. And I'm drawing axis aligned lines, which is a different kind of tree, KD tree. But BSPs do not have to be axis aligned. You can draw a line in any direction you want. We'll call this one line 2. And the splitting plane 2. And then off to the left is a leaf node containing B. And off to the right is a leaf node containing C. All right. And then if you ever do a point contents test, like if you're like, hey, what's here? What's at this point? What you do is you start here at the top of the tree, as you always do with the tree. And you're like, hey, is the point to the left or to the right of the tree? How do I tell if this point is to the left or to the right of the root of the tree, I should say. This is the root of the tree. Okay. So how do I tell if P is to the left or to the right of the splitting plane number 1? There are 10 types of people who love binary trees. So Voss, how do I tell if this point is to the left over here? This is the left, right? Or to the right over here somewhere of splitting plane 1. How do I tell? I want to tell, I'm going to do cross product, yeah. So if I take the cross product, P minus V, and then I can take just a unit vector in this direction, V0, V1, P minus V and V1 minus V0, if I cross product these two things, if I get a positive value, I'm to the left. If I get a negative value, I'm to the right. And so because I get a positive value here, then I iterate down to the right. And then there's no more splitting planes, so all I have to do now is check, is point P here inside of the convex hole I have here? And A could be like some sort of gnarly convex hole, it doesn't really matter. And then I can do like my convex hole test, like this, and find out, is this open space or is this part of a solid wall? And so basically you just sort of iterate down the tree this way. If you're checking this point here, then you would go to the left, and then you'd go to the left again, and then you'd see if point P is within B or not. And so by using a binary space partition, you can kind of iterate down the tree, go to the left, go to the right, go to the left, go to the right, whatever, until you get down to a leaf node. The leaf node might have 1 hole in it. It could have 5 holes in it. There's sometimes like it could be really hard to split 2 objects, like they're really close to each other. So sometimes you allow multiple holes in leaf nodes. It just kind of depends on your needs. But you know, if you have 5 guys in your leaf node, like you got a D here and a E here, these are all convex holes, then you just kind of loop through all of them. Am I within B? Am I within D? Am I within E? Okay. The algorithm to make it is much harder than using it. And in fact, there is I think it's proven that there is no perfect algorithm for making it that can run in any reasonable amount of time. I think it's actually like provably exponential to do an optimal BSP. So there's all these heuristics. Like what they'll do is like so Sean, if you're curious about this, they might like pick the longest edge of any hole or something like that. We're going to use that as our first splitting plane. And then of the remaining ones, oh, that's the longest one. So that's our next splitting plane. And so there's like different heuristics like that where they just kind of guess, and then they'll look at it. You know, do I have like two planes that are like really close to another? You know, like because they don't like making these really like toothpick wedges, because then you start getting floating point errors, right? Like when you cross product something very close to the same direction, you'll sometimes get floating point errors on either side. So they want the splitting planes to be like not pointing in almost the same direction, because then you get errors on the opposite sides. Things like that. It's a pain. The guy that did bridges, his graduate advisor was actually the guy I think that invented BSPs. So it's kind of cool. Do you split the closest together objects first, go off the longest edge, from there splitting is hard? Yeah, like I said, like the heuristic that I read when I was looking at this is you just find the longest edge that, you know, that's in that hemisphere, that not hemisphere, hemi space, whatever. Of all the people that are within, you know, this zone over here, now that we already have CD, you know, if you have a really long edge like this, then that becomes the splitting plane, from what I understand. Okay. There's a lot of work on that. I've never made a BSP myself. I've used them. I've never made them myself. It seems like a lot of work. Maybe I can have you guys do it this semester. That could be fun. It's a good idea, Sean. I appreciate that. I'm kidding. We're gonna do ray tracing. We're gonna make our own ranger, so it'll be fun. So that's it for. Don't you dare pin that on me. I will not partake in your evil. Yeah, whenever students suggest, you know, like a good idea, like, oh, I'll make a homework out of it. Sure, why not? So yeah, making a BSP tree, that can be fun. Or various definitions of fun that don't include actual fun in them. So that's our class today. You guys understand you're going to do linear rasterization by Thursday. It basically just cleaning up the starter code I gave you. That's it, free 10 points. And then due next Tuesday will be triangle rasterization. So you're gonna have to do this algorithm by next Tuesday. All right, and if you're Megan, you know you're the boss, so you're good. All right, that's it for today, guys, and I will see you guys on Thursday. Peace.